Hello everyone, welcome to my channel. Now in this video I am going to discuss the two topics, gravitational potential energy and escape velocity. Now before we go into the details of the topic gravitational potential energy, we need to understand the term potential energy. So let's start the video. Now in the chapter work, energy, power, we have already gone through the term potential energy. Now we have studied that potential energy is the energy possessed by a body by virtue of its position or configuration. Now configuration means shape, like when we change the shape of an object, we do some work on the object and the object acquires some energy. Like if you have a spring and if you compress the spring, that means you are doing some work on the spring and the spring undergoes a change in shape, and that is, it stores energy. The other thing is the energy possessed by virtue of its position. Now that also gives rise to potential energy, and that is in fact related to gravitational potential energy that we will see it now. Now see, there is a term called field. We have gravitational field, we have electrostatic field. So suppose this is a region, this is the field, gravitational field or electrostatic field. Now if you move any body which is under the influence of this field, then you need to apply some external force. Okay, so when you are applying some external force, that means you are doing some work on the system and the system is acquiring energy, and that is the potential energy. So now suppose you have this earth, okay, and this is the surface of the earth. Okay, now suppose we take 2 points which are close to the surface of the earth, that is this radius is r. Now these 2 points are at height h1 and h2. This is at height h1, this is height h2. Now this h1 and h2 are quite smaller than r. Okay, now if they are quite smaller than r, that means the gravitational pull, if they are quite smaller than r, that means the gravitational pull on the object at h1 and h2 will be same. Okay, now that gravitational pull, it is the weight of the body, and that is equal to mg. Okay, so now if the object is displaced from h1 to h2, the work done will be mg h2 minus h1. Okay, now see, this work done depends on the initial position and the final position. It is independent of the path followed while moving the object from h1 to h2. So that means this work done is path independent, and it shows the conservative nature of the gravitational force. So gravitational force is a conservative force, that is, work done by this force is independent of path. It depends only on the initial position and the final position. Now let us consider another scenario wherein you have this earth of radius r and mass m, capital M, and suppose this is a location at some arbitrary location at distance r, and you have a mass m. Okay, this is r from the center. Okay, so the gravitational force on this is F is equal to g m by r square. Okay, this is from Newton's law of gravitation. Now suppose this mass is displaced from position r1 to position r2, then what will be the work done? Work done W will be F dr from r1 to r2. Okay, now what is F? F is this quantity, so this is g mm by r square dr from r1 to r2. Okay. So this on integration we have g is equal to, this is dr by r square, that is minus 1 by r. So if I take the minus sign common, it is minus gmm. This is 1 by r2 minus 1 by r1. Okay, so this is the work done in displacing the object from r1 to r2. So here we see that the expression for work done, it depends on the position r1 and r2. Okay, it is independent of the path followed by the particle. It just depends on the initial position and the final position. Now if we consider this r1 to be at infinity, initial position of the particle to be at infinity and the final position to be at r, so in that case this W is equal to minus gmm by r. So this is the amount of work done in bringing the object from infinity, from position of zero potential energy to given position at position R. Now this is the potential energy at position R. So we'll have U is equal to minus gmm by R. So this is the expression for gravitational potential energy of Earth at distance R from the center. That is, like if you are on the surface, it will be U is equal to minus gmm by capital R. Now at height h, it will be U is equal to minus gmm by R plus h. Okay, so this is the expression for gravitational potential energy. Now you may think that for Earth of mass m, radius r, at height h, you have a mass small m. The potential energy we have now obtained, U is equal to minus gmm by R plus h. But you may think that, okay, but what was then this expression? Potential energy equal to mgh. What was this? Earlier we have learned that potential energy at height h is mgh. Now we are getting it is minus gmm by R plus h. So what is the difference? See, this expression U is equal to minus gmm by R plus h. Okay, this is the potential energy at height h from the surface of Earth. Now see, at low height, when h is much smaller than R, in that case this R plus h can be written as R. So R plus h is approximately equal to R. So in that case U is equal to minus gmm by R. Okay, and what is G? G is equal to acceleration due to gravity is gm by R square. Okay, acceleration due to gravity is gm by R square. So that gives gm is equal to gr square. Okay, and U is equal to minus, so gm is equal to gr square into m divided by R. This R cancels out. Okay, so this is U is equal to minus mgr. Okay, so that is when you are at surface, you are at distance r from the surface, that is when you are at the surface, you are at distance r from the center, and potential energy is mg minus mgr. The negative sign shows the attractive nature of gravitational force. This negative sign is because of the attractive nature of the gravitational force. So now from the idea of this gravitational potential energy, we are going to define the term escape velocity, and we are going to study its mathematical form. So just now we have seen that gravitational potential energy on the surface of Earth. Okay, now suppose this is the Earth of mass m, radius is r, you have a body of mass small m on the surface. So gravitational potential energy on the surface is minus gmm by r. Achha. Now what is this gravitational potential energy? This is the amount of work done in bringing this mass from infinity to this surface point on the surface. So amount of work done in bringing this mass from infinity, so from infinity to the surface is this. So that means the amount of work done in taking this mass from the surface to the infinity will be negative of this. So that is, that work done will be plus gmm. Okay, so please try to understand this. See, this is, you are doing this amount of work done in bringing the object from infinity to this point. Okay, so the opposite of that, the amount of work done in taking the object from the surface to the infinity will be plus gmm by r. Okay, now how do you take this object to infinity? You just can't give this energy and it will go to infinity. You will impart some kinetic energy, you will throw it. So that energy is, suppose that energy is the kinetic energy, so half mve square, and this is the speed it is imparted so that it goes to infinity, and this is called the escape velocity. Okay, so escape velocity, it is the minimum velocity with which an object must be projected so that it escapes from the gravitational pull of Earth and it goes to infinity. So this is the kinetic energy with which the body is projected, and it is equal to g m by r. So this m and this m cancels out, so we have ve is equal to 2 gm by capital R. Okay, this is the expression for escape velocity. Okay, now this can also be written as ve is equal to, this gm is equal to gr square, so this is 2 gr. Okay, so these are the two forms in which you can write the expression for escape velocity. Okay, the numerical value of this escape velocity is, for Earth it is 11.2 kilometer per second. That means if you throw anything with this velocity, okay, then it will escape from the surface of Earth. That object will go away, it will move out of the gravitational field of Earth. Okay, and the other interesting thing is, see, this escape velocity, it is independent of mass of the projected object. See, it depends on the mass of Earth, but it is independent of the object which is projected. Okay, so it is independent of the mass of the projected object, and the other thing is, it is independent of the angle of projection. You can project an object at any angle, okay, but the velocity should be equal to or greater than this, then it will be able to escape. So escape velocity is independent of mass of the object, and it is independent of angle of projection. It does not depend on angle of projection. Okay, but that does not mean that you throw the object, if you throw the object in this direction, it will escape. Okay, you have to throw in a particular way so that it is not able to hit other objects in its path, then it will be able to escape. Okay, so I hope this concept is clear to you, and if you have any doubts, you can post in the comment box, and I hope this will be beneficial for your examination. Good luck.